Good morning. My today's topic is product movement as one of the important rules of bivariate distribution. Now, we have already studied about movement, about origin and movement about mean, but product movement is something which is associated with bivariate distribution and is one of the important tools when we study two variables and the existing correlation between them. So in that sense, product movement is very useful, one of the very useful tools in statistical analysis. Let us start with the definition of product movement of the random variables capital X and capital Y when the variables are discrete as well as the variables are continuous. So our first definition goes like this. The rth and sth product movement about the origin of the random variables capital X and capital Y is denoted by mu r comma s prime is the expected value of the random variable, which is denoted by capital X raised to the power r multiplied by capital Y raised to the power s. And symbolically we write expectation of this variable, which is defined as double summation over the random variables capital X and capital Y. Here I have written small x and small y as which represent the values of the variables capital X and capital Y. The summations are taken over the quantity small x raised to the power r multiplied by small y raised to the power s multiplied by fxy, where fxy represents probability mass function as capital X and capital Y are discrete random variables. The range of these quantities r and s, which are discrete indeed, are from 0 to infinity for both r and s. Okay, so this is known as the product moment, rth and sth product moment of the product of the random variables capital X and capital Y raised to some individual powers. Okay, now if capital X and capital Y are continuous, then in that case, as you know already, that summations are replaced by integration, and we integrate the same thing, small x to the power r, y to the power small s multiplied by fxy dx dy. Now this quantity becomes integrand, and the double integration is taken over the entire real line, one along x-axis and another along y-axis. And you know double integration's geometrical interpretation, which has already been discussed in one of our earlier courses. I am not going into the details of these mathematical expressions because lots of problems have already been done on that. But here the important topic, the important part of this particular lecture is this expression, capital X to the power r and capital Y to the power s, and their expectation value. And just like we represented movement about origin by mu primes, here product movement about the origin have been represented by mu r comma s prime. Similar to that, the product movement about the means can also be defined in the following way. Try to recall the definition of movement about mean. What was that? Expectation of capital X minus mu. That was the definition of movement about mean. So similar to that, the rth and sth product movement about the means of the random variables capital X and Y denoted by mu r comma s is the expected value of this quantity. The expectation of capital X minus mu suffix x raised to the power r multiplied by y minus mu suffix y raised to the power s. And symbolically we write it as this, which is defined as double summation over the values of the random variables x and y, and summation is taken over the quantity small x minus mu x to the power r, small y minus mu y to the power s fxy, r equal to 0 1 2, s up to infinity, and s equal to 0 1 2 up to infinity, if capital X and Y are discrete. And if they are continuous, the double summations are replaced by double integration. Now, to distinguish between product moment about mean and product moment about origin, we have changed the notation. The notations for product moment about origin have been defined as mu primes, and the product moment about means notation have been used as only mu's. So these are the important definitions with which I am going to continue with my today's class. And you remember these expressions. These expressions are very important for our further analysis. We shall now discuss a special case of the definitions which have been stated above. Special case is, let us consider the moment about mean, the product moment about mean first. And let us put r equal to 1 and s equal to 1 in the expression. Now, if r equal to 1 and s equal to 1, so in place of mu rs, we'll write mu 1 comma 1. And capital X minus mu x raised to the power r and capital Y minus mu y raised to the power s will become capital X minus mu x raised to the power 1 and capital Y minus mu y raised to the power 1. So actually we are taking the expectation of the product of these two quantities, which is similarly defined as double summation over these quantities. And similarly, if we consider the random variables to be continuous, this can be expressed in terms of integration. Only thing you have to remember that fxy and fxy, these two fxy's are different. Here the fxy represent the probability mass function if capital X and Y are discrete, and this fxy represent probability density function if capital X and capital Y are continuous. My important part is not about the discussion, the broad analysis about product moments, but about this special case, because we shall be using this special case a lot in our subsequent analysis of statistical situation. Okay, we are mostly interested about this quantity mu 1 comma 1. Why? Because the answer is, this quantity has a special name. This special case of the product moment has got a special name, and that name is covariance between the variables capital X and capital Y, irrespective of the nature of the variable capital X and capital Y. If capital X is continuous, then also it represents the covariance between the two variables. If capital X is discrete, then also it represents the covariance between the two variables. And the covariance between the two variables capital X and capital Y is sometimes denoted by cov of x comma y, and sometimes it is denoted by sigma suffix x comma y. Covariance is the most important part of the formula of correlation coefficient between the two variables, okay, for a bivariate distribution. I can recall that in one of the earlier years, I took a class of statistics for some students, and when I started analyzing the product moment, the definition of product moment correlation, product moment about the origin and product moment about the mean, students said they were too much bored. They were becoming bored about too much discussion of mathematics, so they wanted to jump onto the part of applied statistics soon. And so I had to skip the discussion of product moment. I started directly I started taking classes directly on correlation coefficient, where covariance of xy was used. But because I skipped this particular chapter, I didn't discuss it in the class. Students, the concept of covariance capital X comma Y wasn't clear to that bunch of students. They couldn't understand what is covariance of capital X comma Y. So that's why I'm taking my today's class, is because probably you are thinking that you are also doing too much of mathematics. I'm doing this kind of analysis for the sake of this quantity, covariance X comma Y. y, and when I'll be starting correlation coefficient in this in my next class, you will understand the relevance of today's class. Okay, now here is a problem for you. You look at the problem and you copy it. So the problem has been represented in terms of expression. What do we mean by this expression? This is the given condition. This expression means this, that capital X is a binomial distribution with parameters n comma p. If capital X is a binomial distribution with parameter n comma p, we are supposed to prove the following results. So let us prove it one after another, one by one. Since capital X is a binomial distribution parameter n and p, so immediately we can say that E of X, expectation of capital X, is equal to NP, variance of capital X is equal to NPQ. Because these are the means and variances of the binomial variate, and we have already discussed in the chapter of evaluation of statistical parameters for binomial variable. Now we can divide both the halves by the quantity small n. So we get expectation of X by small n is equal to P, variance of X. Now, and in this equation, we are dividing both sides by n square. Why am I dividing both sides by n square? There is a special reason for that. I'm coming to this point. So we get expectation of capital X by n is equal to P, variance of capital X by n square is equal to n into PQ by n square. So it becomes PQ by n. But if you can remember that I discussed that variance of the quantity C is a constant multiplied by the random variable capital X, variance of Cx becomes C squared variance of X. So when you take out of the constant, when we take the constant out of the variance symbol, it gets squared. I divided the both side by n squared so that I can include n inside the variance symbol, so that I can write variance of X by n squared as variance of X by n. Okay, and why am I supposed to do this in this manner? Because of the questions, pattern of the question. You see, they are actually dealing with the variable, random variable, not of the form of capital X, but of the form of capital X by small n. So after this small analysis, I'm able to write this as expectation of capital X by n is equal to P, and variance of capital X by n is equal to PQ by n. And you just keep this in mind, that I am now considering the variable, random variable X by n. Random variable is of the form X by n. Okay, let us mark it as capital A. Variance of X is defined as E of X square minus EX whole square. Several times we have used it, but the actual definition of variance is this: expectation of X minus EX whole square. What do we mean by that? What is the meaning of variance? Variance means that the average of the deviations of the values from the mean, that is called the variance. Okay, average of the square of the deviations of the values from the mean. So if I translate this word mathematically, we will get this expression. So you see, you just say along me, average of the square of the difference of the variables from their arithmetic mean. So this can be expressed in this manner. I have done a small analysis over here. I have broken the square into, with the help of the formula of a minus b whole square, we get this x square minus twice x ex plus ex whole square. I am now operating the expectation on all of these quantities. So we get e of x square minus e of this quantity plus e of this quantity. So e is the expectation of x whole square is coming inside expectation, another expectation. We will keep expectation of x square as same. But you see, the quantity 2 is constant and quantity ex is also constant, because expectation of any random variable is constant, because expectation represents average and average is constant. So we can take 2 and ex outside the expectation sign and we get 2 into ex multiplied by e of x. Here e of x squared is also constant, because average, if average is constant, its square is constant. So we can take this outside ex square and inside we get e of 1. but expectation of any constant quantity is constant, and therefore E of 1 equals to 1. So we get ultimately this formula. So this we treat as our working formula, which comes from the definition. If V of x equal to E of x minus Ex whole squared, so similar to that, V of x by n will be E of x by n minus E of x by n whole square. Just look at this expression and this expression. Okay, I'm using this over here. But E of x by n, you have already proved it is P. So I can write it as E of x by n minus P whole square, and which is PQ by n, already proved. So V of x by n equals to PQ by n, or E of x by n minus P whole square is PQ by n. So first part is proved. Next, we are going to prove the second portion. Covariance of xy is defined as, denoted by mu1 comma 1. It is defined as E of x minus Ex multiplied by y minus Cy. So covariance of x by n comma n minus x by n is defined as this. We are replacing capital X by x by n and capital Y by n minus x by small n. Now you just look at these two expressions, you will understand. Covariance always comes with respect to two variables. Here we are actually considering two variables. Since capital X is present only, don't think that we are dealing with single variable. Here we are dealing with two random variables. One random variable is of the form x by n, another random variable is of the form n minus capital X by n. So we can treat this as x and this as y. Now, in place of E of x by n, we can put small p. So we have done it here. And this can be written as 1 minus x by n minus E of 1 minus x by n. Now, we can operate E on both these expressions. You know already that E of x minus y is E of x minus E of y. So we can write it as 1 minus x by n minus E of 1, which is 1, minus minus plus E of x by n. So 1 and 1 cancel each other, and we get E of x by n minus p minus x by n plus p, because E of x by n is already p. So these two expressions are same. Only thing we need to do is to take the minus sign outside the expectation. So we are doing it over here. We are taking the minus sign outside the expectation, and we are getting E of x minus n minus p whole square. And what is that? That is E of x minus n minus p whole square. What is that? We have already proved it above. It is pq by n. So ultimately we are getting covariance of this expression becomes minus pq by n. So it is a very beautiful example, and you can treat these two results as a theorem. If you can remember, in some problems it may become a helpful tool. Okay, you can use directly. It's a very important result. Keep this in mind. Next, we are going to discuss this particular theorem, which is sigma xy is equal to mu1 comma 1 prime mu x mu y. You know sigma xy is representing the covariance between the two variable capital X and capital Y. So sigma xy can be written as E of x minus Ex multiplied by y minus Ey. Now here also I am doing the same thing. In place of Ex and Ey, I am putting their values mu x and mu y. These are not the values actually, these are the notations for Ex, and this is the notation for Ey. I'm multiplying the thing. So we are going to get xy minus capital X into mu y minus mu x into capital Y plus mu x into mu y. I'm operating expectation on each of these terms. So we are going to get E of xy minus. Now you see, mu y represent the average of the random variable y. So this is constant. We can take it outside the expectation sign. So we get mu y multiplied by Ex. Similarly, mu x can also be taken outside. So we write minus mu x multiplied by expectation of y. And here, the product of two averages is also constant. So we write mu x mu y. We can take mu x mu y outside the expectation sign. So we are going to get mu x mu y of E1. So this is E of xy minus, what is Ex? Ex is itself mu x, so we can write it as mu y into mu x minus mu x into mu y plus mu x into mu y. A pair of mu x mu y will cancel each other. So we ultimately get E of xy minus mu x mu y. Now what is this? E of xy. Let us scroll up. We know that moment about origin, product moment about origin can be expressed in this manner. So you just see the expression mu r comma s prime is expectation of capital X to the power r multiplied by y to the power s. What will happen if we put r equal to 1 and s equal to 1? We will get mu 1 comma 1 prime is equal to expectation of capital X multiplied by capital Y. The same thing has been done over here. Here, in place of E of xy, we have written mu 1 comma 1 prime minus mu x into mu y. So we have seen that the special case of the product moment about mean has been expressed as a special case of the product moment about the origin when r equals to 1 and s equal to 1. This is a very useful result, and we are going to use this as a tool to solve problems. You very well can recognize this particular problem. We have discussed this problem several times. This problem represents a joint probability distribution of the bivariate random variable. So capital X is taking the value 0, 1, 2, and capital Y is taking the value 0, 1, 2. This right hand side column is the marginal probability of Y. The bottom line is the marginal probability of the random variable capital X. And these green colored probabilities are the joint probabilities. We are supposed to find the covariance between the two variables capital X and capital Y. So let us calculate the covariance. To calculate the covariance, we need this particular formula. So we need to calculate mu 1 comma 1 prime first, and then mu x and then mu y. If we can consider their difference, then sigma xy, that is covariance between the two variables, will come out. How to calculate mu 1 comma 1 prime? Okay. Mu 1 comma 1, oh sorry, there will be a prime sign over here. So there's a mistake. You just rectify this. Or before uploading the note in the Google Classroom, I shall rectify this particular portion. It should be mu 1 comma 1 prime. The prime sign should be there. So mu 1 comma 1 prime will be E of xy. Now E of xy is what? We have to consider the joint variable, the product of the two variables together along with their joint probability. So how to calculate this? You see, I am taking the value of capital X to be 0, multiplying this with the value of y, which is 0. So 0 into 0 multiplied by their respective probability, 1 by 6. Then we are considering 0 and then 1, multiply them together, and then you multiply the product by 2 by 9. So 0 into 1 multiplied by 2 by 9. Then 0 into 2 multiplied by 1 by 36. 1 into 0 multiplied by 1 by 3. 1 into 1 multiplied by 1 by 6. 2 into 0 multiplied by 1 by 12. So ultimately, by this calculation, we get 1 by 6 as the value of mu 1 comma 1 prime. Similarly, to calculate mu x and mu y, we can consider the marginal probabilities. So for mu x, I am taking the values of x. Like I am multiplying 0 by their probability 15 by 36, 1 by their probability by its probability half, and 2 by its probability 1 by 12. We are getting thus the value of mu x. And to calculate mu y, we are multiplying the value of y by its marginal probability. So we are taking 0 multiplied by 7 by 12, 1 multiplied by 7 by 18, and 2 multiplied by 1 by 36. So by this, we get the values of mu x to be 2 by 3 and mu y to be 4 by 9. Now you are in the position to apply the formula. So according to the formula, the covariance will be the difference of these two quantities. So we are writing mu 1 prime's value as 1 by 6, and we are taking the product of 2 by 3 and 4 by 9, and ultimately we are going to get minus 7 by 54. Sigma xy is not probability, so result can be minus. But this has very beautiful physical interpretation, which I am going to discuss in the next class. You keep on thinking that why this result is minus. What does it symbolize? What does it signify? Okay, if the result is, if the covariance between the two variables capital X and capital Y are minus, what does it represent? Just you can take the help from the book also. Lastly, before I conclude my today's class, we are I'm considering this particular problem. This is also known to you, and this is the probability density function. Domains are represented as this. Here also, to calculate sigma xy, we need to calculate separately mu 1 prime, mu x, and mu y. And I'm not going to discuss in details. I have just written their results over here because this problem has already been done. This type of double integration has already been done in our earlier course. You try to solve this by yourself, and you will try to get these results. So here my objective of doing this particular problem was to show you that I can use this result. I mean, let me show you. If my objective was to show you that if I can consider this result can be considered for any type of random variables, capital X and capital Y, which are either discrete or continuous. Okay, so in the theorem, nothing has been mentioned as the nature of the random variable capital X and capital Y. That means it is true for all type of random variables. Only thing you have to keep in mind that capital X and capital Y shouldn't be of different nature. You cannot consider capital X to be discrete and capital Y to be continuous. Okay, then this result will not hold. They are of the same type but of different nature. Like either both of them are discrete or both of them are continuous. The result can be used. Therefore, I actually uh, included this particular problem to show you the objective of finding the way of finding the covariance between the random variable, continuous random variable capital X and capital Y remains same. We need to find these three quantities separately and use the theorem. The result will come out. So you try to verify this result by yourself. Okay, you check the calculation. I have chosen the problem from the John Foynt's book. But remember one thing, that when you study some pages, I've seen that in some pages, let me show you. I have this hard copy of the book with me, and you have the soft copy. But the soft copy is far more better than the hard copy, because I have seen that in this 8th edition, some chapters are missing, as well as in some pages there are printing mistakes. So you be very careful while you study the book. Okay, so for example, in one of the pages I have observed that mu capital X, mu suffix capital X has been written as mu into capital X, which has no meaning at all. So while you study, if you have this hard copy, while study, you just be careful a little bit. Okay, whoever has modified it wrong. So anyways, I have already saved your chat, and today I'm going to end my session at this point. And now we are in a position, we have got so many statistical tools which can be used for our purpose. And from our next class, we are gradually moving to the domain of applied statistics. And I think that now you'll be going to find it interesting. Okay, so mathematical analysis part is complete. Now we are going to apply it in practical situations. Okay, mathematical analysis will still remain there, will be there, but still I will discuss something which are actually part of applied statistics. So I hope you have understood my today's class. And before I start applied statistics with the chapter of correlation and regression, you go through the lectures of product movement of today's class very carefully, and if you have any doubt, you can anytime knock me and I'll clarify your doubts. So till then, bye.